All right, today we are going to continue learning about the angles of polygons. So a polygon is a closed plane figure made up of 3 or more line segments that intersect only at their end points. So you can see here on the left there are several polygons. There are the different shapes and they are closed. On the right we have some examples of non-polygons. So looking at the blue, the reason it's not a polygon because it's not made up of line segments. Anything with curves, circles, would not be polygons. The purple oval is curved, and the orange, it looks, even though it appears to be like a reflection of two triangles, the fact that it intersects in the middle. The other thing that would be considered not a polygon is if you had a shape that was not closed. It was just left open like that. We would not call that a polygon, even though they are made up of straight edges. So in our first explorations of this concept, we came across something called triangulation. And if you recall, in the activity, the online activity, we were taking a polygon and dividing it up into triangles inside. So I'm going to kind of go through and we'll talk about how many triangles are formed inside each of these polygons here. So in the triangle, and the idea of triangulation, and the way I like to systematically do it, even though it's not the only way to do it, is to start from one endpoint. So when you look at an endpoint in a polygon, for instance, this right here, this triangle, you have right here that endpoint connected to the other two endpoints. There are no other vertices to connect it to. Therefore, there is only one triangle formed, is what we found. So there's one triangle inside of there. But when you look at the square, you can see that this endpoint right here, if this is our starting point, is already connected to this endpoint and this endpoint. So we only need to draw one diagonal line to connect it. Therefore, two triangles are formed. Moving on to the pentagon, you would draw two diagonals and 3 triangles are formed. Hexagon forms 4 triangles. Here we get 5 triangles. Say the number and I write the number. That's how that works. Okay. Next is the octagon. So see how I'm just starting. It doesn't matter which vertex I start at. If I connect it to each of the other vertices, then I've broken it up into triangles. And you start to recognize a pattern as we do this, based on the number of sides. So the octagon had 8 sides, and we usually say that the number of sides is n, right? So the next one to the right of that is a nonagon. It has 9 sides, so n equals 9. There are 9 vertices. So if I'm going to draw and triangulate the nonagon, I'm making 1, 2, 3, 4, 5, 6, 7 triangles inside there. Then you have the decagon, so we're running out of names here too. Pretty soon we're just going to start calling these n-gons. And you can see that not only does it become a difficult process to draw the polygon, it becomes difficult to then triangulate it as well. So when you have 10 sides, you have 8 triangles. So here n was equal to 10, and triangles are equal to 8. If you count the sides of the next one, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. N is equal to 11, and the number of triangles is equal to 9 if you triangulate. The dodecagon has 12 sides, and 10 triangles formed. So what you're going to start noticing is this pattern in relation to the number of sides. So back up at the triangle, we had n was equal to 3, one triangle, n was equal to 4 in the quadrilateral, n equal to 5, n equal to 6, n equal to 7, and n equal to 8. Okay, down here, n is equal to 13, and here n is equal to 14. So hopefully you can see the pattern that the triangles will equal 11, and the triangles here will be equal to 12. And in triangulation, if you take n minus 2, you will equal the number of triangles formed inside. Now, why is that important? Because we are going to use what we know to be true with the total degrees inside of a triangle to then calculate the total sum of all the angles in these polygons. Through this idea, the interior angle measures of a polygon, the sum S of the interior angle measures with n sides, is calculated by taking n minus 2 times 180. So the n minus 2 is the number of sides minus 2, and that 2 comes from the two adjacent vertices that any point is already connected to, right? Then you drew diagonals to all the other vertices to divide it into triangles. The number of degrees in a triangle is 180. So let's give this a try. Find the sum of the interior angle measures of the green polygon. So the first thing I would want to do is find out how many sides it has. So I'd count 1, 2, 3, 4, 5, 6, 7. So if n is equal to 7, I know that I could use the formula n minus 2 times 180. So I get 7 minus 2 times 180, or 5 times 180, and that equals 900 degrees inside of a heptagon. Looking at the little honeycomb, 2, 3, 4, 5, 6, n is equal to 6. So 6 minus 2 times 180, or 4 times 180 gives me 700, ooh, that's not a very good 8, 720 degrees inside of a hexagon. And that's true for all hexagons. So now we can use that information to find a missing angle. Now in this case, you're not asked to list all of the angle measures, so pay attention to the directions. And this says find the value of x. Once we solve an equation for x, we're done. But you know, sometimes you find the angle measure and you have to go in and list all the other angle measures, even though you can see them right there, so that makes that job easier. So first we have to know how many sides this is. 1, 2, 3, 4, 5, 6. So n equals 6, or 6 sides. We know that 6 minus 2 times 180 would be 4 times 180. And we just found that out to be 720. So since there are 720 degrees total, I can add up all of the angles. And I can start with x. X plus the 135. I'll go counterclockwise here for this one. Why not? As long as you systematically keep track. Equals 720. I'm running into the next area. So all of these together can get added together. And when I did that, I got 615. So double check to make sure I did that right. X plus 615 equals 720. So if I subtract 615 from both sides, I have found x to be 105. And we just need x, but since it's an angle measure, it's not wrong to put the degree symbol. Okay? Looking at number 4, there are 4 sides. So if n is equal to 4, 4 minus 2 times 180 is 2 times 180, or 360 degrees inside every quadrilateral. Every quadrilateral has 360 degrees. So starting with x, I'll change colors here so that it might be easier to see. We would have x plus 115 plus 80 and plus 90 to equal the 360 degrees. Again, the like terms. So x plus 285 equals 360, and I'll subtract the 285 on both sides to get finally x is equal to 75. And again, it was a measure of one of the angles, so I can put the degree symbol. The last example, 1, 2, 3, 4, 5, where n is equal to 5, so we have 5 minus 2 times, that doesn't even look like a minus, so 3 times 180, and that's equal to 540 degrees. So we have, in this example, 2x plus 145, I'm going to run out of room, plus 145, plus 2x plus 110 will all equal 540 degrees. Okay, so combining the like terms, here I'm going to use some circles because I have some variable terms here. So I know that I'll have 4x plus, and then all of these numbers are all positive, so I can add them together. 145 plus 145 plus 110 will give me 400. And if I add those together, I get 540. So I start by subtracting the constant. So 4x is equal to 140. Divide by 4, and x equals 35. Now in this case, x itself is not a degree, so I definitely don't want to put the degree symbol. I do know that this angle measure is 2 times 35, or it's equal to 70. So I can leave the degree symbol off the x. It's a lot of work, but if you take your time and start with the total sum inside the polygon, you should be successful. Alright, the next thing is finding the measure of each interior angle of a regular polygon. Now, this idea of a regular polygon is defined as all sides are equal and therefore all angle measures are equal. So think of some regular polygons like the equilateral triangle or the square. You know, you could have a regular pentagon, you can have a regular octagon, looks a lot like the stop sign. So, and the octagon is the first one. So in the octagon, it's the same formula. In this case, we're going to start with the total sum, where you take the number of triangles times 180, and since every angle is the same, divide it by the number of sides. So since in an octagon, the number of sides is 8, you would do 8 minus 2 times 180 to find the total sum, or the total number of degrees. So 6 times 180 is 1080, and then we have to divide by the number of sides, which is 8, because they are all equal. And so each angle in an octagon is 135 degrees, and that's what they're wanting to know. Okay, a decagon has 10 sides. So if n is equal to 10, we have our 10 minus 2 times 180. 8 times 180 is 1,440. Now let's divide it by the 10 angles, because they are all equal to each other. And we would get each angle measure at 144 degrees. And you definitely want a degree symbol. In the last example here, an 18gon. This is where we start talking about where we don't have special names for it. So we generalize it and we call it an n-gon, where n stands for the number of sides. So by looking at this name, we know that n is 18. So you can substitute that in. 18 minus 2 times 180. You'll get 16 times 180 for the total sum of all the angles added together, 2,880. And to find one measure in a regular 18gon, we know they're all equal to each other. We can take that divided by 18. So each angle is obtuse. This is where it becomes more and more difficult to draw these polygons. Okay, the last main idea that we're going to be working on is the total sum of the exterior angles in a polygon, any kind of polygon. The sum of the measures of the exterior angles in a convex polygon is 360. So if you stop and think about that for 1 minute, it's kind of like the exterior angles add up, and if we were to cut them up and put them all together, it's kind of like the degrees in a circle, 360. You do a full revolution. So w plus x plus y plus z equals 360. So let's find the measures of the exterior angles. Now, please note that in this equation, problem, you're not asked to find x. You're asked to find measures of exterior angles. And since it's a pentagon, there are 5 sides and 5 vertices. There are 5 exterior angles that we have to find. We know that they all add up to 360, so it doesn't matter where I start. If I start at the top, I can say 90 plus x plus 90 plus 90 plus x equals 360. So just double check that you covered all vertices. So I have 3 right angles and 2 x's. 1, 2, 3 at 90 degrees and 2 x's. So then combine your like terms to add, to simplify the equation. So 2x plus 270 equals 360. Subtract 270 from both sides. 2x is equal to 90. Last step, divide by 2, and we find that x is equal to 45. Great, we found x. Now we have to list all angle measures. So we have our 90 degrees, we have a 45 degrees, 2 more 90 degrees, and 1 45 degrees. And so this becomes our total answer. Okay, don't just stop at solving for x. Finish the problem. Okay, so for your homework, you'll be working it out of your book on page 123 to 125. Do 4 through 8, 12 to 26, only the evens on that. And it's also available as an online assignment through your bigideasmath.com. But remember, record your answers on paper for in-class grading.